Let's talk about the quantitative aspects of acids and bases. Previously, you've learned about the autoionization of water. And so, what that really was trying to illustrate was that if you have water molecules together, there are going to be, out of billions of water molecules, collisions between them, and a few will be at the correct orientation and have sufficient energy to actually cause a proton, meaning a hydrogen ion, to be transferred. And in solution, you will have hydronium ions and hydroxide ions. So that is the autoionization. And evidence has actually shown that fewer than two molecules in about a billion will actually ionize to do that. So what we see is that at standard ambient temperature and pressure, so at SATP conditions, the ionization constant for water is equal to 1 times 10 to the negative 14. So that means if we were to take the concentration of H3O, the concentration of OH, we multiply them together, we will always get that constant. Again, we have to be at SATP conditions. So what we would see then in solution at that particular temperature, the concentration of each of those ions would be 1 times 10 to the negative 7. Multiplied together, that's how we get 1 times 10 to the negative 14. So what we can do is we can use that information to aid in determining whether a particular solution is acidic or basic in nature. And so what we want to do is take a look. If we have these two ions in solution, and they are equal, then we would say that we would have a neutral solution, something that has a pH of 7. If something is acidic, we know that this concentration of hydronium ions must be greater than the hydroxide ions, and so we would know then the pH is less than 7. We don't know the exact pH, but we just know that it is acidic in nature, and vice versa for the other combination. So let's see how we can use the autoionization of water constant to help us determine whether something is acidic or basic. And again, this particular problem is also found on page 535 in the textbook. So in this scenario, it asks you, what are the hydrogen ion and hydroxide ion concentrations in a 0.15 mole per liter solution of hydrochloric acid? So what I do in that particular case is I take a look at the acid in the formula, and I use a straight arrow because it's a strong acid, and I show the ions that it dissociates into. Now you can write it like this, but we now know the more appropriate way to show the dissociation of an acid is to show that aqueous means in water, in solution. So I'll just write the water here, but we can see that this hydrogen ion from the acid actually gets donated to the water to form hydronium and chlorine. Okay, so what we want to do is we want to make note that this is a 0.15 mole per liter solution. In knowing that that is 0.15, we know that it is 1-to-1 with each of the ions that it dissociates into. So that means the concentration of the hydronium ion is also 0.15, and so with the chlorine ion. Okay, but we're just interested in this one here. So we have got that one done. So hydrogen ion is the same as hydronium ion, means the same thing. What we do is we use this relationship. The Kw is equal to 1.0 times 10 to the negative 14. And we know that that is equal to the concentration of the hydronium ion times the concentration of the hydroxide ion. Because we know this value, we can rearrange and we can solve for the hydroxide ion concentration by dividing the constant by the hydronium ion concentration, which we know is 0.15. So if I go ahead and replace that with 0.15, we end up with a hydroxide ion concentration equal to 6.7 times 10 to the negative 14 moles per liter. So now we have the hydroxide ion concentration. We can also determine whether this is an acidic substance or a basic substance by comparing the hydronium ion concentration to the hydroxide ion concentration. Hydronium is 0.15. Hydroxide is much smaller, 6.7 times 10 to the negative 14. So because this concentration, the hydronium, is greater than the hydroxide, we would say, therefore, this is an acidic substance. Okay, let's take a look at the next question. The next question tells you that you have 2.6 grams of sodium hydroxide dissolved in 500 milliliters of distilled water. Calculate the hydrogen ion or hydronium ion concentration and the hydroxide ion concentration. So what we need to do is we need to take a look at this particular compound, which is NaOH. And again, I can write it with water as the reactant, or the AQ means the same thing. So here we see that this is a strong base. Remember that this is an alkali metal with a hydroxide is strong. We use a single arrow to show it dissociates into its ions, 100% dissociation. This is a 1-to-1 relationship. So for every one of these that dissociates, you get 1 sodium, 1 hydroxide. What we need is to know the molar concentration of sodium hydroxide before we begin. They give us the mass and they give us the volume. So we must calculate concentration equals moles over volume. We don't have moles, but we can replace that formula knowing that to calculate moles from mass, we need mass divided by molar mass on the top, and we have volume in liters on the bottom. What I will do is I will go ahead and take 2.6 grams divided by the molar mass of sodium hydroxide, which is 39.997 grams per mole. Divide by the volume. Now the volume I want to convert into liters, so that is 0.5 liters. When I end up completing that calculation, I end up with a value of 0.13 moles per liter. Okay, grams cancel out. There we go. So what we've just solved for is the concentration of NaOH, 0.13 moles per liter. That means we know the concentration of the sodium ion is also 0.13, and the concentration of hydroxide is 0.13 moles per liter. So we have done the hydroxide ion concentration. We're going to use the ion constant for water. So knowing the relationship, Kw is equal to 1.0 times 10 to the negative 14 is equal to the hydronium ion concentration times the hydroxide ion concentration. If we know that this is 0.13 and I want to isolate hydronium ion, I bring this to the other side and divide. So I would divide by 0.13. Okay, and in doing so, we end up with a hydronium ion concentration of 7.7 times 10 to the negative 14. So from this, when we do a comparison of the hydronium ion concentration and hydroxide, we can see that 0.13 for hydroxide is much bigger than 7.7 times 10 to the negative 14. And therefore, this particular solution is basic in nature. That's how we use the autoionization constant for water in order to help us determine whether something is acidic or basic. Now, what we've come to realize is that this seems to be a bit awkward, using such tiny quantities to express the strength of acids and bases. And someone decided that this way is too confusing and has developed the concept of the pH scale to help us determine whether something is acidic or basic. So what we're going to learn about in the next video is how to determine pH. And there's also something known as the pOH scale that I'm going to introduce you to, which is a much easier way to determine something that is acidic or basic.